Good morning everyone. We are there in the lecture number 10 today. However, before going there, probably it is a good idea to give a brief review of what we have discussed in previous lecture, that is lecture number 9, because these two are kind of tightly related to each other. So, let us overview quickly what we discussed, and there was kind of small mistakes in the slides also. So, that will also correct that actually. So, this is what we are talking about, how do you convert it from state space representation to transfer function representation, and vice versa when you have a linear systems. So, here it is, I mean what we discussed last time is when you have a state space representation x dot equal to x plus bu and y equal to cx plus du, and this is what the transfer function form that you are looking for. Then you started with this equation here, and then carried out Laplace transform for both the equations, and then eliminated x of s from first equation, substituted it back here. That is what we carried on there. So, then it turns out that y of s is given by this final expression out here. Okay. So, this is c into s I minus a inverse v plus t, and that is the transfer function matrix in general we are talking about. Remember, there are multiple outputs and multiple inputs out here. Okay. So, this is in general y is a vector and u is also a vector. So, in principle we cannot talk about y by u anymore, but some books write that way, y by u, and then they give it as a transfer function matrix. Then there was examples, we carried out that examples and showed that if this is a linear system, a 2-dimensional linear system, then that is what the transfer function is all about actually. It's straightforward to derive it from the formula, which we carried out detailed algebra here. And we also made some points that this converting the transfer function to state space is rather not unique, whereas the reverse one is very unique actually. Okay. So, we have I mean there are various realizations possible, and we also made a note that all realizations are equivalent actually. That means the basic properties do not change. However, one representation may have some advantage over the other for a particular task actually. So, a lot of research has gone into that in around 50s and 60s. How do you get good realizations actually? So, possible representations that comes to mind is first companion form, otherwise known as controllable canonical form, and we also discussed what is Jordan canonical form last time. Okay. And then in this particular class we will talk about alternate first companion form, which is called as the Toeplitz first companion form also, because of the matrix that it pops up actually. And then we will also see what is called a second companion form, and otherwise known as observable canonical form. Okay. So, for example, if you want to design a controller, then controllable canonical form is a better option, whereas if you want to design an observer or a filter, then observable canonical form turns out to be better choice actually. So, then we had this okay, we started with this transfer function y of s by u of s, then we multiplied both sides. Okay. Then if you multiply, then that is the differential equation that pops up, and that is in I mean the same thing that is written in elaborate form. Then you chose these state variables x1, x2 up to xn that way, then differentiated and ended up with these equations actually. So, first n minus 1 equations differential equation will simply come from definitions, and the last one will come from the differential equation that we are having here actually. Okay. So, that is how we got this first companion form, which looks like that way. Okay. And because y is nothing but x1, so the C and D matrix turns out to be just this actually. Okay. So, that is how we ended up with first companion form. We also briefly overviewed this block diagram representation, which essentially requires n integrators, because you have an nth order differential equation anyway. Yeah. So, that is the reason why you require this n state variables really. Anyway, so then we had further examples where we talked about this transfer function. What is this is a third order polynomial. So, we have essentially a third order system. So, we defined the x1 to be c and x2 to be c dot and x3 to be c double dot like that, and then we carried out okay, these are the state space representation or state space equations that way actually. So, then we moved on with a polynomial in the numerator. What do you do about that? then we decompose that into two blocks rather. First block will give us the same differential equation that we just derived before, and the next one will give this particular thing will give us the output equation actually. Okay. So, this is how we arrived at this kind of forms and all that actually. So, this is the realization with this particular side, that the output equation contains all these 172 sort of thing actually. All right. So, how do you generalize this to multiple outputs? These are all about single outputs anyway. So, if you have multiple outputs, then essentially the A and B matrix remains same. However, the C and D matrices gets modified actually. Okay. Also saw example to demonstrate that, where this one is the y1 of s divided by u and this is y2 of s divided by u. These are the transfer functions that we are talking about. So, note that this denominator is same. So, here we decompose this particular this y1 by u as these two variables that way. Okay. So, this 2s plus 3 falls outside of these. Okay. So, these are essentially two cascaded blocks what we are talking about here. And then the first part of the block gave us the state space representation, and the second part of the block will give us the output equation actually. Okay. So, that is how we got the output equation for y1, and similarly the output equation for y2 will be this way. Okay. Whereas the state equation, the A and B matrices will remain same actually. Okay. All right. Then we also reviewed what is known as we went through in detail what is known as Jordan canonical form. Okay. So, if you have a transfer function in general already factored into this form, okay. Okay. If it is not factored, then the first thing is to do this factorization actually, and assuming that this factorization is already available, okay, then with we multiplied again this y of s is equal to all that, and then we define these little expressions as x1 of s, x2 s, x2 of s like that up to xn of s. That is definition, and simply from definition this differential equation pops up like that. Okay. And hence we already have a state space representation of the system dynamics x1 dot up to xn dot actually. Okay. So, that is how we got it, and then y turns out to be all this, y is summation of this summation this plus this all these expressions. So, but these were nothing but x1 plus x2s then up to xn s like that. So, the y of s simply turns out to be this x1 plus x2 plus up to xn plus d0 times u. So, this is our C matrix and that is D matrix actually. So, these two are essentially A and B matrices. So, this is the Jordan canonical form, and we also had that okay, this is an example where you have this non-repeated roots sort of thing. Then it is essentially straightforward what we discussed, and that landed up with this A, B, C, D matrices actually. Okay. D is 0 here. So, A, this is A, that is B, and this is C matrix here actually. Now, what do you do when you have repeated roots? Okay, that is a special case probably, and then we define these state variables that way. Okay. So, x1 is nothing but x2 by s plus 3, this is a cubic polynomial, remember that. So, x2 is x3 by s plus 3, and then finally x3 is u of s by s plus 3. So, again from these simple definitions these state equations pop up actually. Okay. Then the output equation is slightly interesting to see here. The output is essentially this entire thing multiplied by u of s. Okay. So, then if you analyze that a little bit, this u of what you have here, okay, I can expand in an expanded form, I can put it there. Okay. I just write it that 3 times essentially 1 by s plus 3 into 1 by s plus 3 into 1 by s plus 3 like that. But we note that this is nothing but x3 of x. Okay. So, if once I put x3 of s here, then it turns out to be like x3 of s by s plus 3, which is nothing but x2 of s, and once I put x2 of s here is nothing but x1 of s. Okay. So, essentially y of s turns out to be just 2 times x1 of s. So, noting all these, that these are the state equations and this is the output equation, we can finally convert all these into time domain and tell okay, this is my Jordan canonical form A and B matrices, and this is the corresponding C and D matrices actually. So, that is how we got for repeated rows. Up to that probably we studied with some slight corrections of the slides and all that. And then we also note that there can be one more complexity in Jordan canonical form, and that happens when this factorization form the roots become complex actually, and we do not want this matrices of A, B, C, D elements of these matrices to be complex numbers. We do not want that. That is not a real realization for real systems actually. Okay. So, what we really want is real number sitting out there actually. So, how do you do that? And also this observation comes to our rescue here actually, that if the roots become complex, they can always exist in complex conjugate pairs actually. Okay. And interestingly, this let us say the only one particular form, we have something like 2 repeated roots out here, and they are in complex conjugate pair actually. Okay. What you see it here, and interestingly corresponding to that you will also have numerators as complex conjugate pairs actually. Okay. So, all these nice observations give us a hope actually. So, what do you do? If you just combine them together, okay, then the complex part goes and you are left out with a real transfer function actually. But remember this in a factorization form I cannot write that anymore actually. So, what I can do that rest of the transfer function elements, what rest of the factors I will do the regular Jordan canonical form, but this particular this particular conjugate pair roots I will go ahead with some other companion form like first companion form for example. So, this particular block I will write it in a regular first companion form that we have discussed already before. Okay. However, the other things will turn out to be Jordan canonical form actually. Okay. So, that is the way to do. So, this is all about some overview of the previous lecture. So, that we will carry on with the further things in this class actually. So, the last lecture we saw this first companion form and Jordan canonical form. I will continue our discussion with further things here with first thing is this an alternate first companion form or sometimes called as Toeplitz first companion form. We will see that why this name pops up actually, and this is the reference for that where I have taken it from here actually. Okay. So, we will start again with the transfer function, okay, in this form, okay, and then we can again multiply both sides, okay, and then write it in the standard differential equation form here actually. Okay. So, this is nth order differential equation both in y as well as u actually. Okay. So, this is a very generic thing actually. Okay. This is a proper transfer function, but they need not be strictly proper. Okay. Proper transfer function means the order of the numerator polynomial is less than equal to the order of the denominator polynomial. Okay. So, in this case you are taking it like equal, that is the best that you can have actually. Okay. In general, this order of the numerator is much lesser than the order of the denominator actually. So, that is a proper strictly proper transfer function rather actually. Okay. Anyway, so once we write this differential equation form for this output and input relationship, now let us define the state variables x1 to xn in such a way. Okay. So, how do we define? Let us say output we will define that as x1 plus p0 u. This is simply a bunch of definitions actually. Okay. And we write x1 dot, okay, is x2 plus p1 u and x2 dot is x3 plus p2 u like that actually. Okay. These are all state equations. Remember, if I somehow know this p0 up to pn, then I am done actually, because this is my output equation, okay, and these are my state equations already known to me actually in a way. So, it is my task to get this constants p0, p1, p2 up to pn, that is the task actually. Okay. So, but we will go back to this definition, okay, start from y probably. Okay. So, y is nothing but x1 plus p0 u, and then we take first differentiation let us say. So, that is y is y dot is nothing but x1 dot, okay, that is simple, okay, times p0. Remember, p0 is a constant number. So, it turns out to be p0 times u dot actually, but x1 dot by definition is nothing but x2 plus p1 u. So, this is coming from here. So, I can substitute that x1 dot here, okay, and then retain this p0 times u dot. So, that is what I leave with actually here. Now, let us go to y double dot, one more derivative out here. Okay. So, I start with this expression rather. So, this is x2 dot plus p1 times u dot plus p0 times u double dot. So, that is what it is actually. Okay. Then x2 dot is again I will go back to the set of definitions and substitute from here. X2 dot is nothing but x3 plus p2u. Okay. So, x3 that x2 dot is x3 plus p2u plus these two I will keep it as it is actually. Okay. And note that when you have y, there is a u, when you have y dot, there is a u dot expression, there is a y double dot, there is a u double dot expression. So, that is how it will pop up actually anyway. So, I will carry this sequence of operations and then I will end up with y n minus 1/3 order derivative, which will turn out to be like this. Simply by observation perhaps I can write something actually. If I see this y, this is x 1 plus this y dot, this is x 2 plus p 1 plus p 0 u dot, then y double dot is x 3 plus p 2 u plus p 1 u dot plus p 0 u dot u double dot. So, I mean if you see that there is a trend out here, it is a y double dot, it starts with x 3, then there is a p 2, p 1, p 0, there is a u dot and u double dot actually. So, continuing with that trend I can probably generalize this and then write it, and I can also verify that actually. Okay. So, this is this will turn out to be like this. The small dot mistake, probably there is a typo mistake. So, let me correct that. There is a dot out here actually. It's in dot actually. Okay. Probably. Okay. So, anyway. Anyway, so that is that's what it is. So, I will go back to nth order. I mean. Then I'll from here I will stop and I will substitute okay, this I mean I will take one more derivative and then carry out this algebra properly actually. Okay. So, y n, remember that y n will come from this definition actually. Okay. Y n is I will take everything to the right hand side, okay, and all these derivatives are available to me right now. So, I will substitute all these. Okay. And then I will carry out with this algebra. You can probably sit down with the equations and then try to see what is going on here actually. Okay. Probably I mean there is a small correction here, probably this this dot is I mean this is probably not necessary, that is what it is actually. If I see y double dot, there is a okay. If I see y double dot, it starts with x 3. If I say y dot, it starts with x 2. So, if I see y n minus 1th derivative, it starts with x n. There is no, the dot is not necessary basically what I mean. Okay. So, I will carry out and then I will put this when I take one more derivative, x n dot will pop up here, and then going back to the equation, this is my x n dot. Okay, this is the simple definition for part of it. And then I mean this x n then this expression will come into right hand side, all that, and then I will combine all this. This is a longhand expression actually, the last equation. So, up to that we have to be slightly patient to see what is going on actually. Okay. All right, now I am ready because I am ready with all these definitions y dot, y double dot up to y to the power nth derivative. Okay. So, then I will go back to this equation what I started with, that is my objective anyway. Okay. So, this entire equation is available to me. So, I will just simply plug in all these expressions actually. Okay. I have all these expressions anyway. So, once I plug in okay, this is the left hand side and the right hand side part of it, okay, this right hand side all these expressions whatever available, okay, this all these things will also come to right hand side and things like that. Okay. What I essentially mean to say is you just plug in all these things, okay, and try to simplify these terms. And interestingly, it turns out it will just retain u dot, I mean all these powers of u only actually. Okay. Once you substitute for all these variables, let us say, okay, if you can I mean you can do this algebra here, because this term, all these terms that is there here, okay, that will try to kind of I mean this is try to help you in simplifying this expression, and it will have you, I mean it will lead us to some expression like this actually. Okay. But this expression what you see in the first line, okay, that is nothing but this expression also, that is the transfer function anyway. Okay. So, this transfer function, if I mean this expression is equal to that expression is also equal to that expression. Okay. This expression comes from the transfer function actually. Okay. So, what I do now, I mean if these two have to be equal, okay, this expression has to be equal, then I can equate the coefficients actually. Okay. So, whatever if I have u, then that is equal to b 0, then this coefficient what I have, that is equal to b 1, and similar thing all the coefficients I can equate to, and then I will end up with a set of equations actually. So, if I go in a little reverse order, let us say, this is u to the nth power actually. Okay. So, what do you have actually nth order derivative and not really power, but this is also nth order derivative here actually. Okay. So, you have this P 0 equal to V n actually. Okay. Then the next equation, this what you have P 1 plus this expression is nothing but V n minus 1, like that actually. Okay. So, I will say constitute a construct a set of equations. Okay. Now, this set of equations, if you see, this has given me sufficient number of equations, that is, if you count number of equations, it is actually 1 to n, okay, plus 1. Okay. That means, what I have is n plus 1 equations, and I also have n plus 1 variables starting from P 0, P 0, P 1, P 2 up to P n, that is n plus 1 variables. So, I have n plus 1 set of equations for n plus 1 variables actually. So, I can essentially solve this. So, if I want to solve it in a vector matrix form, so these equations I will first put it in a vector matrix form, and that is what I will do actually. The first equation is simply P 0 equal to V n. So, that is 1, everything 0 is equal to V n. The second one is a n minus 1 P 0 plus 1 times P 1 is equal to V n minus 1. So, that is how it is actually, a n minus 1 P 0 plus P 1 is equal to V n minus 1. That way I can construct this actually. So, this is the set of equation, and here that is why this name Toeplitz comes, because this is particular, if you observe this matrix, this is a lower triangular matrix essentially, and this specific form what you have is called as the Toeplitz matrix actually. Okay. And the interesting property out here is actually it is not necessarily only a lower triangular matrix, but the diagonal elements are all 1, that is the difference actually. Okay. This is a lower triangular matrix. Okay. All other elements can have arbitrary numbers, let us say, but the diagonal elements have to be all 1 actually. Okay. Now, as you know, if I really carry out this determinant evaluation of this, any triangular matrix, the determinant is nothing but product of diagonal elements actually. And since all diagonal elements are just 1 out here, so the determinant is guaranteed to be 1, and hence it is always guaranteed to be non-zero. That means, no matter whatever values I have for a 0, a 1 up to a n minus 1, whatever values I have, this matrix is guaranteed to give me a solution, this equation is guaranteed to give me a solution, because this matrix is guaranteed to be non-singular actually. Okay. So, solution always exists. So, then I can always invert this matrix and get a solution, or this is already, you can see that I can very well use Gaussian elimination, it is already in the triangular form actually. So, Gaussian elimination is a quick way to get that anyway. So, this set of equations essentially give me the solution, and hence I am done, because once I know this, as I told in the beginning, from the simple definition we have already constructed the state space form actually. Y is already known to us, C matrix is given from here and D matrix is just P 0, and then this bunch of equations x 1 dot to x n already gives us the form that we desire actually. Okay. So, that is so combining them all together, after I get the solutions for P 0 to P n, I can simply write it, these differential equations in state space form to be something like this actually. And interestingly, it turns out that this is also like a first companion form. If you remember the first companion form, this is all super diagonal elements are just 1 1 1, and then we have this last row some numbers, and then the slight difference is this first companion form had all 0 0 0 and the last element was something, but here it is all something or other is there, some numbers are there all over the B vector actually. Okay. Other than that, I think all the things remain same. So, that is why it is also called as an alternate first companion form and sometimes called as Toeplitz first companion form. Okay. Note that even though these are all first companion form, if you write the regular first companion form that we discussed, or controllable canonical form rather, that is called it that way, then the state variable, the matrices can be fairly similar, that means they are very close to each other, the appearance wise actually. However, the numbers corresponding to that will be different, as well as the physical meaning of the state variables will be different in two different forms. Okay. And that is in general that is true. If you realize the system in form 1 and form 2, then obviously these systems, these definitions of the state variables are different depending on the form that you are selecting actually. Okay. So, that we should keep it in mind always actually. Okay. Now, if you really want to do a block diagram realization, okay, let me do that quickly out here. So, this block diagram realization turns out to be rather straightforward here. All right, what we have here actually, we will go back to this this set of equations and try to construct something from here actually. Okay. Just remember this set of equation, y equal to x1 plus p0 u, x1 dot is I mean that kind of a thing actually. So, maybe okay. So, for my benefit, let me do this way. So, this is see, remember this is sorry. So, this is the set of equation that you want to represent in block diagram form actually. So, probably I will start with some y definition, let us say this is x1 plus p0 u. So, I will start with some integrator which will give me, let us say, okay, this will take x1 dot, okay, and it will give me, let us say, x1, okay. That is the form that I am looking, and then remember there is y, what I am talking about, okay, y is nothing but this x1 plus p0 u basically. So, x1 is already available. So, I have to get a p0 u somewhere actually, okay. So, this is plus, and then I will talk about something like a multiplication by p0, okay, and there is a u, okay, this is a u, okay, this is a u out here, control term, okay. So, let me take it all the way and then multiply that and then pass it through actually. So, that is what I will get y essentially. Okay. So, this is our like that part we are done actually. Now, we will come back to this x1 dot is nothing but x2 plus p1 u. So, I will go that way. Okay. So, then this is okay. So, x1 dot is available here. So, I have to construct this x1 actually, x1 dot out here. So, then I will talk about okay, p1, it has to pass through the p1 block, u is already available actually. So, this is a p1 block, okay. We will come through that, and then there is something like x2 basically, right. So, if you see this expression one more time, this is x2 plus p1 u actually here, okay. So, I got this p1 u, then I have to construct this, I have to take this x2 out here actually, okay. And similarly, I can construct, see if you x2, then obviously it has to pass through the integrator actually, and then it I will get x1, x2 dot rather here, it is not double dot, x2 dot actually, okay. So, that way I will be able to construct, keep constructing the top portion of it, and then if I come back to this this side of the story, okay, I have to ultimately construct something like x, okay, this has to start with let us say xn, okay, and then obviously the input has to be xn dot, okay. Then if it is xn dot, remember that it is from the definition point of view, xn dot is just all these actually, okay. So, this entire thing has to be realized actually, up to xn minus 1 dot there is no problem, but this entire thing has to be realized. So, what I do, I will take this x1 is available to me. So, I will pass it through this a0 out here, and x2 is available to me out here. So, I will take it there and pass it through this a1 out here, okay. So, I will construct these things actually that way, okay. And then I will have summation blocks actually all over, okay. I will have summation blocks all over, and then I will take it this one, and then it will go, and this will talk about there is a final summation block somewhere here which will connect it, okay. Okay. This will give me this negative sign, and this will come through some sort of a Pn, okay. This is Pn, okay, and this will connect that actually, okay. This is positive side. So, this will construct xn dot actually, okay. So, remember and this even xn I have to take it through, okay, a n minus 1, and then I have to construct some sort of a summation block out here with positive signs actually, okay. So, if you go back to this and try to correlate this xn dot is nothing but Pn times u plus summation of all this with a negative sign actually. So, that is what we have done actually, okay. Pn times u, it has come from this side, and then summation of all these that we are talking about actually, okay. So, that is why that is how we construct block diagrams and things like that actually, okay. So, it is not that difficult to realize a block diagram sense actually, okay. And let us carry on, move forward with that. So, this is what is called as Toeplitz form actually, okay. So, in block diagram we have just drawn actually anyway. Now, there is some comments out here. Okay. If you see this this differential equation or this block diagram also, whatever you have here, essentially they represent n integrators anyway. Okay. So, that is given in this differential equation as well actually. Okay. So, that is that's easy to see actually. So, no matter what realization you talk about, if the transfer function is of nth order denominator polynomial, then you certainly need a number of integrators like n actually. So, you need n integrators to realize that actually. Okay. Now, extension of the why this particular form is kind of interesting is because if you have MISO system, that multiple input but single output system, okay, then what you the extension is fairly straightforward, because you can always go back to this this form of definition. So, you start writing another set of equation. Let us say for example, I can always write this is like P 0 U 1 plus Q 0 U 2. Okay. So, this is like P 1 U 1 plus P Q, let us say Q 1 U 2 like that actually. So, this is P 2 U 1 plus Q 2 U 2 like that. So, I will set a construct another set of another set of constants or parameters that I need to solve actually. So, the extensions the analysis will be fairly straightforward. I will end up with two sets of equations like that, but both the sets will lead me to this Toeplitz matrix and all that, where solution is guaranteed to exist actually. So, all these things are very nice to this particular form is very nice to extend to multiple input, but single output systems actually. Okay. So, the essential going by the argument that we have just discussed, it essentially one need to solve m system of linear equations, where m is the number of input or control variables actually. If you have m control variables, then you have m such systems matrix equations to solve for actually. However, if you know the number of states are not changing actually, that means we still need n integrators actually. Okay. And remember, if you remember the last class that we reviewed in the the first couple of minutes back in this lecture as well, if you have this multiple output case, but single input case, that going by the first companion form, okay, that was easy to generalize actually. Only the output equations were changing, number of states were remaining constant and the same actually, that means we still need only n integrators actually. Okay. So, the message here is we have this multiple input but single output, we still need n integrators, and the reverse case where you have single input but multiple output, we can still realize the system with n integrators actually. But the entire ball game changes when you have MIMO system, that means multiple input multiple output system, then that is no more true. We will just discuss have a few comments a little later in this lecture actually. Okay. Before moving ahead with the generalization MIMO thing, let us talk about the other form that is available to us actually, and that is second companion form or observable canonical form. And this particular form, as I told in the beginning, is useful when we have when you have to design some sort of an observer or a filter actually, that is some observability and all these properties are nicer in this form actually. Okay. So, how do we go about and do that? So, we start with this same transfer function in generic transfer function, in general that is again the same order. So, we have this proper transfer function what we start with, and then we again multiply these two sides. Okay. And then we talk okay, we will now start looking at this equation in Laplace domain itself in a slightly different way actually. Okay. How do we do that? Now, let us arrange these terms this way actually. Now, I take all the terms to the left hand side and I will start taking the powers of Sn minus 1 like that actually. So, if I take these two terms, this entire expression goes left side. So, s to the power n is here, s to the power n is here. So, I just take that one common and then y of s minus bn times u of s. Okay. So, that will pop up here actually. Okay. So, I am writing everything as kind of polynomial of in terms of s actually. So, s to the power n multiplied by some polynomial, s to the power n minus 1 multiplied by some polynomial like that actually. This is the same equation anyway actually. Now, after doing that, I just want to extract this first term actually. Okay. This first term is nothing but everything to the right hand side divided by s to the power n actually. Okay. So, when I start doing that, then s to the power n is the highest one. So, the first term will pop up as 1 by s actually, next term will be 1 by s square like that actually, and that is what is happening. Okay. So, this is okay, there is a small print mistake maybe, let me correct that. Okay. This term is probably not necessary. Okay. This is a double type actually. Okay. So, if you solve this equation here, okay, this entire expression, okay, here you just take it, you want to extract this expression first from rest of the things. So, you are taking everything to the right hand side, dividing by s to the power n actually. So, this term is not required at this point of time actually. Okay. So, then this is 1 by s to the multiplied by that, next term will be 1 by s square multiplied by that particular term what you have here, the next term what you have here, and things like that actually. Okay. So, now let me analyze this expression a little bit carefully actually. Okay. So, this is actually, if I see this expression, okay, now from here I will try to, I am just trying to extract what is y of s actually. So, this expression, this b n times u of s will come right hand side, okay, from here onwards, not here actually. Okay. So, this is what it is, plus 1 by s into all these terms, plus 1 by s into another term, 1 by s square into that term, all the way up to that actually. So, if I start taking 1 by s common from rest of the terms, I can do that, because these are all higher powers of s actually. First is 1 by s, next is 1 by s square, next is 1 by s cube, like that actually. So, I take 1 by s common here for all the expressions. Okay. Then if I next set of equations, I can take again 1 by s common for next set of equations, like that. So, I am just interpreting this in a nested way actually. Okay. So, 1 by s into multiplied by everything else. Okay. Then the next term onwards, it is still 1 by s multiplied by everything rest of the terms actually, like that. Okay. So, in a nested way I am interpreting that, and now I will start defining terms actually. So, what I am defining? I start defining, okay, this entire term what I see here is nothing but, let us say x1 s, x1 of s, the entire term that I see next in the bracket is nothing but x2 s, like that actually. Okay. So, if I start doing that, okay, so let us with this expression, let us try to draw the block diagram again, then that picture will start emerge a little bit more actually. Okay. All right. So, remember that this is the expression that we want to put it in a block diagram form actually. So, let us draw this, start doing that actually. Okay. So, what we have here is essentially like again that I will put that top side as something that u signal is available. So, wherever I want I can get it, and then this is like again this I will put that as p n, and then I will take it as addition of two signals, and then I want to construct y out here actually. Okay. So, let us see what is y out here actually. Okay. Y is nothing but b n times u of s, okay, what you see here, plus x 1 of s actually. Okay. The entire term, remember, is x 1 s actually. Okay. So, b n times u of s is already available to me, this is u, okay, this is b n. So, that is available. Then what I have is simply x 1 here actually. Okay. So, obviously, if this is x 1, then if I pass it through a integrator, then this has to be x 1 dot actually. Okay. But remember, this x 1 dot is nothing but if I go back to that expression basically. Okay. So, this x 1 dot if you see that the rest of the term is x 1 dot, remember there is integral 1 by s transfer integration actually. So, if I just take out the integration, okay, then the rest of the term is nothing but x 1 dot actually. If I take this term as x 1 dot, then pass it through an integration 1 by s, then I will get x 1. Okay. So, this entire expression what I see is nothing but this term, okay, plus this x 2 of s actually. Okay. Whatever I have, this is x 2 of s essentially. Okay. So, like that I can let us say I can construct it quickly. Okay. So, what I have is let us say x 1 dot. So, I have this let us say p 1 terms, and then it will go there, and then it will have this, then this is okay, this will have x 2, then obviously there is a integration there, then that will have like x 2 dot, like that actually. This series is anyway same for rest of the things. If you have one series of equations, will have like x 1 dot, pass it through integration, it will have x 1, and then x 2 dot, pass through integration x 2, like that actually anyway. Okay. So, if I see this, then ultimately what I look forward is can I realize this x n dot. Okay, that's where it will okay, x n dot okay, integrals pass it through x n actually. Okay, then this this particular thing will give me what is going on here actually. So, this I will take it as some a n minus 1. Okay, and then it will pop up something like this. Okay, and then I'll this loops on the top side will pass it through p n, and here is one summation out here, this plus thing, this will become everything else will become a minus thing here. Okay, and then I will pass it through this case actually. Okay. Okay, there is a whole chain of equations out here actually anyway. Okay. So, if I right this is how. Okay, now x 1 I have this a 0. Okay, a 0 turns out to be like this, and then x 2 when I have this will be like I will take a 1, this is a 1 out here. So, these two guys will be you can sum it up there. Okay, like that actually it will turn out to be like that. So, rest of the things probably you can fill it up also actually, okay, in a detailed way sort of thing. Okay. This is the type of block diagram that we talking about out here actually. Okay. All right. All right. So, if you look at these equations essentially, okay, what are we getting? I mean either these equations right here or through the block diagram out here. Okay, whatever way you can interpret that way. Then what you are getting here is something very straightforward. Okay. So, y equal to x 1 plus b n u. Okay, that's fine. Okay. Then x 1 dot is essentially x 2. Okay, this is the x 1 dot, remember that the entire expression that is there, and then this expression out here. Okay, this expression is nothing but x 2 actually, entire thing actually, this is x 2 of s. Okay. So, that is so if I have x 1 dot I have to cater for this term and this term actually essentially. Okay. So, x 1 dot is nothing but x 2 minus a 1 y plus b n when b n minus 1 u actually. Okay. So, x 1 dot is this one minus this plus x 2 basically. Okay. So, that is what I have it here x 2, first I write x 2 and then these terms are there actually. Okay. So, then I go ahead and try to simplify these expressions. I mean this if I substitute y, because y is already available to me, okay, then I can expand this expression, because this y is nothing but that. So, this will turn out to be minus a n minus 1 into x 1, okay, that's the term that you are looking for. Then a n minus 1 into b n term actually. So, that is the term that you are looking for actually. Okay. So, this I mean just by putting this expression for y, whatever you have, we will be able to expand it that way actually. Okay. So, what are we learning of? We have y expression that way, we are having x 1 dot, x 2 dot all the way up to x n minus 1 dot popping up that way actually. Okay. And x n dot turns out to be simply that actually, because x n dot, if you see this equation, okay, this is probably easy to see from the block diagram. This is x n dot actually. Okay. So, what you see as x n dot out here, okay, this is the x n dot term here, and this x n dot term, okay, this x n dot out here, what you see nothing but these two terms actually, p n times u, then minus times all these expressions actually. Okay. So, what you get here is actually like x n dot is all these two expressions, b 0 times u minus a 0 times y actually. Okay. So, anyway, you can looking back to that, I mean this what I mean is all these expressions are available to you now actually. Okay. Because y is again I will substitute that way, whatever y expression I have here, okay, and then if I substitute that, that is what I will end up with. So, what we observe here is a nice form out here. Actually, x 1 dot contains x 1 and x 2, x 2 dot contains x 1 and x 3, x n minus 1 contains x 1 and x n, like that actually. Okay. So, then you can try to put that in the matrix vector matrix form sort of thing. What it turns out here, because all these dots will contain x 1 actually. Okay. So, that means this column vector is non-empty, all these column vectors will pop up. Instead of a row, what you get is a entries in first column rather actually. Okay. That is the difference between observable canonical form and controllable canonical form actually. Okay. And then this corresponding B matrix is full actually, because everything is a function of U also basically. Okay. So, all these entries will have some numbers all the way actually. Okay. And then simply from definition, y is nothing but x 1 plus b n times u, that will give you the C and D matrix directly basically. Okay. So, that is what is happening actually. So, essentially in this observable canonical form, we will be able to realize this A B and C D matrix that way actually. Okay. The difference is in controllable canonical form, we had a row of entries, in observable canonical form, we have a column of entries in the A matrix actually. Okay. And these are also nicely related to this, like if you see this controllability observability check, that we will study little bit later. We will see that this I mean appearance of elements come handy actually for calculation of this, for checking these conditions that are necessary, like the rank of the matrix and all that actually. We will see that later what I mean. Okay. So, this is the observable canonical form actually. Okay. Now, this first point I have already talked, okay, that they appear in a column instead of a row. An extension of the second companion term to single input multiple output case are possible. Okay. This particular form what you are talking about is possible to extend that for single input multiple output as well as multiple input to single output cases etc. Essentially these two. But these will not study in detail, these are probably beyond the scope of this particular course actually. I will give a reference at the end where people are interested, they can see that this further details and all that actually. So, and as I told in the beginning, the controllable canonical form is good for control design, whereas the observable canonical form is good for observer or filter design actually. Okay. All right. So, now some final comments sort of thing. So, what you have seen? We have seen both single input, single output systems. I mean the SIS sort of thing. That's why we started all these realizations, and we essentially started with nth order polynomial in the denominator, and we saw that they require end integrators. However, there are realizations possible that for single input and multiple output systems, we can still realize the system within n integrators. And for multiple input but single output systems, we can still realize the system with n integrators also basically. Now the question is, what about this MIMO systems, multiple input, multiple output systems? Will it be possible to realize that as well with n integrators? Okay. Now remember, that is not a tricky answer. I mean that is not a very straightforward answer actually. And unfortunately, it turns out the answer is really no basically. That means, it is still not possible to do that with n integrators alone actually. Okay. Now, then what is the I mean immediate answer that comes to mind? So, one way to realize these MIMO systems will be use a number of structures, like whatever form we select, we will see either a SIMO form or MISO form, we will use a number of them in parallel, and especially if u belongs to this m dimensional vector and y belongs to this p dimensional vector. That means, there are m elements of u and p elements of y, then it is always possible to realize such MIMO systems in something like n into, okay, remember n is the number of state variables in SISO system basically, that is what it is, n into minimum of these two basically, that either I will take the minimum of this dimension of u and dimension of p, and then if I construct n, I mean remember one of that form I will choose actually, whatever form that is, I mean that gives me the minimum number, and that is either I will choose something like a form which is extendable to m kind of multiple output case easily or multiple input case easily. Okay. That with using that particular form, I will simply, I mean it is obvious that we need n into that particular number, minimum of this m and p, that many integrators to realize that actually. So, that many state variables are necessary to realize these MIMO systems in general. However, there is a problem out there actually, okay, because that particular thing turns out to be slightly over actually. I mean we probably do not need that many. Okay. So, the question is it possible to do it with a smaller number of integrators, fewer integrators, and the answer is yes, you can do that actually. So, that essentially leads to the question of minimal realization or sometimes minimum realization, some books write that way. So, what I mean is like this is we can certainly do. The question is can we do it even with pure integrators? Then why it is so important, why necessary, why are you interested in even looking at that question actually? And the answer turns out to be that because a non-minimal realization, suppose you take more number of integrators than necessary, then it can either lead to some very odd situations like non-controllability, non-observability or both actually. That means either you cannot design a controller or you cannot design an observer, or sometimes you cannot design both actually. Okay. So, in addition to this numerical complexity, remember this okay, that also comes to picture, because this is the number of integrators is essentially the number of state variables that you need. And remember, the number of state variables essentially is n, then the dimension of A matrix turns out to be n by n. So, if you have extra number of state variables, the dimension of the A matrix, V matrix and all they starts expanding in a big way actually. So, if you have instead of 3 states, you have let us say 5 states, then you have instead of a 3 by 3 matrix, we will talk about 5 by 5 matrix, and essentially the number of elements goes from 9 to 25. So, it's a lot of computation actually. So, we can actually, I mean, can we avoid that the too many computation? That is one thing actually. But more important case is we will also simultaneously lose controllability and observability, which is even worse actually. Okay. So, it may essentially cause theoretical and computational problems, and as a computational problem I was just explained, that means if you have more number of states, the dimension of the problem increases, the dimension of the various matrices increases, and then we are ending up with doing too many computations than necessary for whatever control design, controllability analysis, everything else actually. But more than that, these are more serious issues. For example, if the system is non-controllable, then we cannot just design a controller, no matter what method you use actually. Okay. Similarly, that if the realization turns out to be non-observable, then we cannot design an observer or we cannot design a filter actor actually, and these are more serious issues actually. Okay. So, there are solutions. I mean, the people have thought a lot in 1960s, late 60s and 70s as well. And there are several algorithms exist for finding minimum realization. That means, I mean, you start with probably a little higher order and then you try to eliminate this number of variables that are not necessary, and you are essentially looking for some variables which are linear combinations of other variables actually, so that you can eliminate them. So, these algorithms do exist for finding minimum realization, and then the corresponding ABCD matrices as well. But all these details we will not study in this particular course actually, and anybody who is interested for further reading, they can always refer to this book. It is a very seminal book anyway. This is written by Thomas Koilath, The Linear System. It is a very seminal book for linear systems actually. So, anybody interested in doing further and further studies, they can probably read this book actually. Very nice book, but then it is also mathematically rigorous. That means, if somebody is not very strong in mathematics and things like that, this book may not be that much readable actually. Okay. So, with that small comment, I can probably stop here for this lecture. Thanks a lot for the attention. Next class we will move further with some different topics actually. So, assuming that this conversion between transfer function and state space and vice versa is possible in a variety of ways. There are other forms also we will not discuss. Anybody interested, as I told, they can always refer to this Thomas Koilath book actually. Thanks a lot.